Okay, that concludes the first talk. We now get to the second talk. So now we welcome Elias Bareinboim from Columbia University, where he directs the Causal Artificial Intelligence Lab, and his research focuses on causal and counterfactual inference and their role in artificial intelligence and data science.
Thank you. Good morning, everyone. Thank you for the call, the talk hall. Very nice. It's a different, yeah. Thank you, the organizers and Michael, for the invitation. A pleasure to be here. I'm not about planning, but I'll talk about causal reasoning that is very related. I'm Elias. I'm a professor at Columbia University, and I lead the Causal X labs. We work towards making AI systems that preserve the remarkable linguistic fluence of the systems. I think I will characterize as they're doing pretty well in this dimension, while becoming more causal, more reliable, and safer. I would be happy to speak with people that are interested, with anyone that is interested on this direction. In particular, today, I'm talking about a gap, what I believe is a structural gap in how you build these systems. I'll try to argue that this gap has a precise diagnosis, and I also say that I'll try to explain how the formal theory of causality can provide a tool for us to address it. And let me start with a picture of a cat, and I give this image to a state-of-the-art model, the ones that we're discussing here earlier today, and ask one of the simplest counterfactual queries, and I will define what is a counterfactual, but in human language for now, using my NLP here, my language fluency, what would happen if the cat pushed the vase off the table? And this is the result that we got. Now, we don't need to be a causal researcher or AI researcher to see that there is something wrong here in this scene. This is from GPT, and this is Nano Banana, the Google version of it. The note here, and I will elaborate more on that through the talk, maybe 20 minutes from now, look the pillows around, if you haven't noticed yet, and the pillow disappeared, at least in the left. And there is this strong correlation between pushing the vase, right? Pushing the vase off the table, and we want to fulfill the signal and see that something broken. Now the LLM is doing something they didn't expect. Now the question for us is about what's happening here. And by the end of the talk, or in the middle of the talk, I think we start having idea about what's happening and why it doesn't matter to have bigger models or more data. It's not a bug in reality. That we can kind of scale it away, but there is some kind of something deeper going on here. Now, but there is something striking here, that the same kind of tech, and I would usually say that these models, some kind of 10-year-old, may be able to find that there is something that is implausible or not reasonable in the picture that I just showed, but it's something interesting that has happened. The same kind of system that is failing in this kind of 10-year-old type of question are making things extremely well. Then let me start the talk with taking a step back and trying to look where we are, and starting with the good news. Systems are able to perform extremely well in making predictions in high-dimensional settings. In particular, there's huge progress in the field of natural language, some progress in the field of vision, computer vision, and some progress in the intersection of RL, as discussed earlier. We can discuss the degree. Applications are everywhere. I don't need, the conference is very big nowadays, and I don't need to tell you this to you guys. And this is amazing. This is like awesome, and we're very happy to be in this situation. Now, the question that I like to ask myself as an AI scientist is the question about, does this mean that we are done? And I usually like to do the Gedanken thought experiment that is about understanding that is not true. Let's assume that we have infinite amount of compute and data. Let's entertain this idea. Compute is not the problem and data is not the problem, in the sense that I will specify. Then does this mean that we are done if we have that? And if not, what is missing? Now, this is the other side of the coin. There are still challenges here for this AI. There are still serious foundational issues. I have been saying that for a few years now, but I'm very glad to see that some of the leaders in the field that brought us to the situation that we are today. The remarkable breakthroughs are starting to acknowledge that. Maybe not, it still didn't percolate in the whole community, but this is a quote by Ilya saying that just very recent, just scaling is not enough. We need new ideas for the next jump. I would say we have the ideas, but still, let's take it that scaling is not enough from the call, from the quote. Now this is Ian saying that scaling alone will not get us to systems that understand the world. Now the key word here is understand. I can do a review on Ian's himself understanding, but let's stick with scaling alone will not lead us to understanding. This is Yoshua saying, another Turing Award, saying that robust and safe AI requires causal understanding. Without it, systems will fail unpredictably. Now you can be friends. He mentioned the causal understanding. I'm very happy. Key word here in reality is fail unpredictably. We are mostly computer scientists or AI engineers. Things will fail. There's a no-brainer. This is our lives. The question is unpredictably, and also what are the outcomes of these failure situations. But anyhow, there is a growing feeling, a consensus, at least in some of the thought leaders in the field, that people that brought this technology and do the translational type of science, that there is something missing in scaling another solution. I understand that it takes some time for the whole community to synchronize. Now I would like to elaborate on this point. Current AI, zooming in a little bit about what could be the issues, current AI systems suffer from, I would say, lack of understanding, again, the same word, and inability of providing explanations. Explanations about the world or explanations about the systems themselves. I'll elaborate over each one of them. They are very prone or suffer from potentially unfair and unethical decision-making. I usually like that when I'm teaching kind of more basic AI or ML, as we have these big classes. There is this service at some point, a few years, that I think we do for the students, that you say, give us more data, and eventually things will be okay. And it's almost like an axiom or a very strongly held belief that more data will solve all the problems. Now, breaking news or comment here, data is nothing more than the picture from the reality that you are sampling from, that you're observing, number one. Number two, reality is messed up. That's the breaking news. There's many problems. There's skewed bias, and there are many problems in reality. Now, if you're training AI with the data that is sampled from this reality that is messed up, again, no PhD required, what do we expect that will happen with the AI? AI doesn't have, in principle, a strong bias as a tabula rasa type of thing. AI is just kind of capturing the regularities that are in the data. Then I usually say that this is a punch in the face when I put my AI ML standard hat, that data is the solution for all the problems. They are very data inefficient. We need many times billions of data points in order to train something that an infant will take with very few. Then there is some kind of fundamental mismatch here about how things are happening in terms of training, or some kind of, we're trying to think to fit something in a slightly off way. They are also very poorly generalizable and lack of robustness. It's not very hard to make, Raul was earlier saying, but it's not very hard. There's some cell, there are some brain that require, but not so hard to find examples that the systems will break. I never been in this room, still moving here. I already can kind of leverage information, and some I would call more technically, some of the causal invariances that we have in other rooms that I made presentations, and I'm operating here as if I already talked here a few times. And they also, my last one, there's a lack of controllability. It's very hard to go to this latent space with 1 billion or 100 billion parameters, change a few bits and steer the system in a direction that we want to make sure that to move, because there is kind of lack of structure there. We kind of change one thing and we ended up moving the system in a different direction. Those are kind of very thorny and long-standing problems, I would say, at least most of them, not new, but the degree of dissemination that the systems have in society kind of raised the flag that you should be more serious, even aware of them. Maybe some of you haven't heard about some of these problems, aware, and then kind of more serious to try to tackle them. The question that I ask myself is also, do these problems have anything in common? Is just Elias here coming and have a bag of problems, or is there a structure there? And my claim, EB here, Elias is speaking, that at the core of these challenges is the absence of a robust causal understanding. Now, if this diagnosis is right, is correct, then the central question is how can we build more trustworthy AI systems? My argument will be is that we should take an approach in the same way that we take in science. We should try to a scientific approach for understanding, and what the keyword, what understanding means. And in science, we don't only observe and try to fit the data, not only observe the regularities, we also intervene. We also provide real explanations, not the spurious explanations as trying to mimic tokens or the trajectories I said before. It's kind of mind-blowing in a way, and very cool. We also intervene. We also explain things in a proper way. We're also reasoning about alternative realities, a counterfactual, about the multiverse, about the different versions of reality that could have been. Then that structure is largely missing from the current AI, as I will argue. The question then is how to build this type of capability about reasoning, about interventions, about providing explanations, about reasoning counterfactually. The question is how to build that into the AI systems. This is why I would like to move towards a more scientific type of approach for AI. Now here's an idea about how to do that. I would like to model the agent-environment relationship through causal language. And this is the cartoon here. We have the real world, and then we have the agent that is interacting in the world, typical picture. But now we have a quote by Turing, which kind of started the field, saying what we want is our hero here in our computer science community, with computer science folks. But he said, what we want is a machine that can learn from experience. And that's very nice. In spirit, I think it captures what we want. If you want my quibble here, more than that, my fundamental, the word experience is overloaded. There is too much things going on what experience means. And I would like to open up different types of experiences that the agent could have in the world. These are called the EB unpacking here. One type of experience is about the agent could be just there sitting at the moment you're sitting and kind of passively observing the world. We call that true seeing, through passive observations. A second type of way that we could experience the world is by intervening. Maybe you go into the world, you kind of start tinkering things, shaking things up, to understand what are the effects of your actions. Both of them seeing and doing are kind of very physical or active in a way. The third one is like we can run our simulations and our model. You can imagine these different versions of reality and learn through that. A lot of the learning happens inside the box, inside of the cognitive system. Now it turns out, interesting enough, that these different types of capabilities or types of experiences that we could have, it turns out that there is a different formal language, computer science here is speaking, the abstractions and languages, there is a different formal language related to, fundamentally different formal language related to each of these modalities. In the field of causality, that maybe you haven't heard about, this is called the Pearl-Causal hierarchy, due to, in honor of you, the Pearl, also a Turing Award, and I will just call the PCH, for simplicity. Many words, very similar to what we have, the Chomsky hierarchy, or the P versus NP, very common in logic and mathematics that we're trying to understand limits of something or basic semantics and expressive power and trade-offs in computation. It turns out that this is an orthogonal language. I'll cite my book later, but it's almost like orthogonal to the idea of computation itself. There is another dimension that is statistical complexity, computational complexity, and there is a dimension called causal complexity, or about the understanding that you have about the world. This hierarchy is about that, orthogonal to sample efficiency and computation. Now, summary of these slides that not all experience is created equal. I would like to first let me do a citation. This is discussed, general book here, scientific dissemination book. If you haven't heard, it's called the Book of Why, that explain how causality is important for humans and maybe kind of intertwined even with our identity and what differentiates us from other species. And I think it's a good recommendation. Yeah. Now, observation here. Once we have a causal model or a collection of causal mechanisms, this induces a PCH. That is different types of experiences that we have. The first one that I already mentioned is the one that is called related to seeing, related to passively observing what we have. Symbolically, where is my mouse? Give me a second. Yeah, symbolically, you have this P of y given x. Given that you observe x could be a long sequence, 1 million dimension x, I would like to know what's the probability of the event y, or the next token if you want. Or observe an image, a set of pixels x, 100 by 100, and I would like to put the label. Now, in machine learning, this is very related to the idea of supervised and unsupervised learning. We kind of, it's all about doing computations on top of this probability distribution. Depending on the decade that we live and how we read history, very important, we were chatting earlier during the coffee break, there is a different formalism that allows us to do evaluations of expressions such as P of y given x. Maybe in the 90s or the 2000s, you have the Bayesian network. At some point, even before, you have variations of probabilistic, maybe support vector machines, or decision trees, or, I don't know, the 2000s and so, you have the deep neural nets. Now, this decade, we are in the one related to the transformers, and that we are able to, question here that I usually get, parentheses, but then why you have so many of them, Elias? Yeah, it's all about scale. We are talking, already have semantics to quantities like P of y given x, maybe 200, 300 years old. Now, what's the difference? Now you can handle objects with billion dimensions, or 100 million dimensions. Before you couldn't, then we were doing our kind of typical computer science type of job of scaling something up. But semantically is exactly the same. Right? We were computing a posterior distribution. Nice? Now, but this is not everything about the world. This is just one type of experience. The second type of experience is related to interventions. You have symbolically different type of distribution that we're talking about. This is the P of y given do x, comma c. You observe a context C, you do an intervention, physically intervene in this physically, quote unquote, intervene in the system, and you observe the outcome y. Very related to the human activity of you doing, with your own muscles, you did the interventions. The machine learning counterpart for that is called reinforcement learning. Different formalisms you can use to describe and to do inference on top of distributions like that, such as a causal Bayesian network, not a Bayesian network, but a CBN, a MDP, a Markov decision process, a partial observable, a POMDP, and so on. The very good specific way of doing inference about this layer. Note for the RL folks, given that we're in the planning here, then there is RL people. Very peculiar and very amazing, but very peculiar in specific way about how to sample from this, how to get causal information from the world. It turns out that there is much more than just sampling through a typical RL setting. Check the causal RL. I'll share my book later. There is a whole part there that is dedicated for the causal RL. I digress here. But the third capability, or the third type of experience, is related to counterfactuals, or the idea of imagination. How can you do retrospection, introspection? What are the principles behind this, the idea of imagination? What is the code that is running there, underlined when we are doing that? Let me just pass, where's my mouse? Oh, here. Let me just parse here one symbol here, or one sentence in this language, because it's different, or very different. We have the x prime and the y prime here after the conditioning bar. I could say that Joe took the drug, that big X is equal to x prime, and he's dead. Big Y is equal to y prime, is there, x prime and y prime. Now, this happened in this world, in the factual world, and then you can wonder, would Joe be alive? That is y, that is the opposite of y prime, had he not taken a subjunctive, had he not taken the drug, that is the subscript there, had it, x different, the opposite of x prime. Now you can already get the vibe that there is no experiment in the world, not even in principle, that we can conduct. By the way, this is one that in the real world, not in the necessarily RL world, but in the real world, it is possible to sample from the distribution do x, comma c. The FDA, the American FDA, we run randomized control trials. We spend each control, RCT, randomized control trial. Each RCT that you run in the real world costs $5 million, $10 million, 100, 200 people or so, and we are able to sample from the distribution. 99% of the data in the world is coming from distribution in type 1. 99% of the data. There is peculiar cases that you can sample from distributions type 2, like such as the FDA setting, or if you're at Google, you can do A/B testing and so on. But distributions type 3, this one, impossible. Unless we can do time travel. And 1 millisecond before you give the drug to Joe, you submit Joe to the alternative condition and run, right? See how reality unfold. In principle, you cannot sample. We don't have data from this distribution. This should be clear. Still, very fundamental notion. Counterfactual underpins this idea of imagination, or the notions of credit assignment, blame, responsibility, understanding at the end. Then very important, the question, how do you compute that? How do you evaluate expressions like that? In the real world, in machine learning, there is no counterpart for that. I call it the structural causal model, the object that gives semantics to quantities like that. Very related to I just mentioned the Book of Why by Pearl and Mackenzie, very related to why type of questions, why something happened. If I say that the probability of Joe being alive had he not taken the drug is, I don't know, 99%, then humans will be satisfied saying, why did Joe die? Joe died because of the drug. Then you can sue and so on. There's all the legal implications there. Very related to the type of question here, I'm here, what if I had acted differently? I didn't, but this still provides some information for us. Was it the aspirin that stopped my headache? It's a question. What is interesting here, technical note here, the formalization of the causal hierarchy, the PCH, provides a way to measure the capabilities, the expressiveness of different formalisms with respect to increasingly complex queries or questions about reality. You keep going from layer 1 to layer 2, layer 2 to layer 3, you get more and more fine-grained information about the world. And through the PCH, it's almost like a standardization, because someone shows a crazy model, it's very hard to compare models. This, I like to think about a way of comparing. Does the model have the capability of providing answers in the different layers of the query in a valid way or in a sound way? That they can say that they will provide? Yeah, 100%. They will say whatever you want, as we discussed or we know. In any case, so going back here, so what does it take to build systems that can reason in all 3 levels of the causal hierarchy? And this leads to the main goal here, main research goal. The goal is to develop a more general AI capable of the following capabilities based on the hierarchy. First one, addressing the 5 bullets that I have as the challenges. First one, we like them to have causal and counterfactual generation. Generation is the G of GPT, that is the sexy topic that people want to discuss nowadays. We also would like them to have causal understanding and the ability to articulate explanations, both about the world and about themselves, why they are doing things in the way that they're doing, and also how the world works. They would like them to be more efficient and precise in terms of their decision-making, not so sample inefficient, right? We need so many data inefficiencies, as I said earlier. You would like them to be more generalizable and robust across these different changing conditions. The world is kind of changing, and we cannot train in everything in a way. And you also like, if you have a baby AI, you would like the system to be able to do learning and discovery, right? To start learning about causality, what are the mechanisms underlying the world from the beginning, from the ground up. Now, this is nice. I'll go over some of them, given the time. I spent the whole year, by the way, in the university going over that and the book in reality. Each one is a different part of my book. I'll share it. It will be in print in the end of the year. The draft is already available. I'll share it at the end. This is the causal and counterfactual generation. This is the picture that I showed before. We already kind of discussed, but the system, just recall, the system is very tempted to try to realize this signal. There's a strong correlation between pushing the vase off the table and something being broken. And then I'll go as far as removing the pillow in order to fulfill this signal, realize this. For us now, we have notation. Layer 1 signal is a correlation between the words pushing the vase off the table and something being broken. They co-occur in the world very frequently. But this is not a fluke. I have hundreds of examples like that. This is another one. If you're sleeping, take a look. We have an abajur there, a lamp. And I don't know if you can see based on the illumination, but it's disconnected. And then there's a button there as well that is off. And then you ask, what would happen if the switch on the desk lamp were turned on? And this is what we got, right? This is GPT, maybe a month ago, and this is Nano. That is the Google version of that. I think it's, don't need to say. Let me show another example. Coke bottle, and there's a carpet there. There's an invitation to the bottle. Then you ask the simplest counterfactual question, again, 10-year-old. Image what would happen if the Coke bottle were knocked over. We can already get the feeling, right? The word knocked over strongly correlated to some kind of spillover. Then they want to realize the signal. The model generates something like that. And this is the nano banana. Now, the question for us is what's really happening here. Yeah. Now I would like to use the building blocks that we discussed to discuss why this could be happening, at least in a high level here, to connect with the PCH and the causal mechanisms. There is this underlying reality that's called, humans call nature, and there is a collection of causal mechanisms there. These causal mechanisms, this is what I said 3 slides ago. These causal mechanisms induce the PCH, the causal hierarchy. Causal hierarchy have the observational layer, the type of experience that you are passively collecting data. We have interventional data, the exponential number of interventional distributions, or how you can manipulate things in the world. I can intervene in the variable x1. I can intervene in the variable x2. I can intervene in the variable x1 and x2, and x3, and x1, and so on. Interventional number of yellow distribution, and even more, super exponential number of counterfactual distribution, because there is different routes about how this reality could have unfolded. Now, this is all encoded in the SCM, the structural causal model, collection of mechanisms I call M star. Beautiful. Everything clean when you have the collection of mechanisms. In the real world, we don't. We just have traces, something concrete that is the data that in 99% of the case is the red type, is observational. Now I have the challenge, unobserved. In other words, the yellow is mostly unobserved, maybe all unobserved or mostly, and the green, unobserved, because those are different versions of the world, and you already talk about Joe taking the drug and being dead. Now, what we are really doing here, the cartoon, what we're doing, we are training a neural model, M hat, in principle, a transformer at the moment. Maybe in 5 years from now, it will be XYZ. And that 10 years ago is a deep neural net. Is a M hat, still the same kind of model, probabilistic model, layer 1. And this model has the potential, this is why I left it open, to induce these different types of experience. Now, what we do, L1, L2, L3, layer 1, layer 2, layer 3. Now, what we do, you train the model. Training here means we spend a few $1,000,000, we dance, you pray, you move around the model. On the other side of the pipeline, there is this Frankenstein, the little monster that emerges. No one know what the monster did. We just hope for the best. And we check things that are embarrassing that happens in the past that will not happen again. And then you put the object to run. Now, what we did during training in reality is to make M hat to match the distribution that you saw, that is the true distribution from the left side. And now the question becomes, but what should we expect about the distributions that we haven't seen? For example, the interventional ones. Then I call this the fundamental problem. Let me just read the problem statement here. Under what conditions inferences in M hat, that is in the right side, are valid? In other words, when do they recover the distributions induced by the true model, the guy in the left, the M star? Now I call fundamental problem of Gen AI, of causality, I would say, of inference or science. Now, of course, we can have different versions of this problem. Another one, I showed the Coke bottle, the lamp, and so on. This is a layer 3 quantity. And I didn't add here, but you could have partially yellow. It is true that, again, FDA is one example. There are other settings, such as humans, that you sparsely do interventions in the world. Then let's use that in some way. But still, interesting inferential task. You partially observe red, and you fully observe red. You partially observe yellow, and now let's split yellow from observe yellow 1 and yellow 2. Now the interesting inference is about, I have red and yellow 1, I want to do inference about yellow 2 or green. The causal inference about this inferential task. If you are doing inference, you get red, and you want to do inference about red, you don't need to talk with me, or you don't need to read the causal inference book, because we are protected by law of large numbers, central linear theorem, some kind of inequalities. All the machine learning theory and statistical theory is about this type of inference, not causality. Causality will use that eventually. Causality is particular about this inference that's across the PCH or across these different types of layers. Then beautiful problem. This is about causal generative model. Let me move. How much time? I have 11, yeah. Let me move to causal understanding and explanation, just to give an example, or a few examples. Again, this is divided in 2 parts, as I mentioned earlier. There is explaining why, how the world works, why things happen in the world, and how the agent works, why the agent is doing things. I will start with explaining why in the context of the world. This is a real example, by the real data analysis here, US Census 2018. This is chapter 8, chapter 6 of my book. You have, for example, the variables that you are measuring is gender and salary. And the data science team or the AI engineers observe that the total variation, the TV, the difference in salary, Y, between males and females, there is a disparity there. I think the number, in a few slides I'll show it, but I think it's 14K. Now the question is like, why this is happening? Should I sue as an employee? Should I sue the company as a scientist, a social scientist, or economist? Why the disparity? And important or not, this is the data. Data is a layer 1 data. Disparity is that. There's a correlation there. They are not independent variables, salary and gender. Now the question is why it happens, and I would say the disparity could be explained through very different mechanisms, could be realized in the world through very different ways. The way type 1 is about maybe in the world, in the real world, people are looking the gender, and based on the HR or the boss, look the gender of the person, and then decide to change the salary. And there is this, what we call in causality, this direct effect from gender to salary. This is option 1. Mechanism 1 in the world that could be active. Mechanism 2 is about gender may be affecting education. For example, have a PhD or don't have a PhD, and education in turn may be affecting the salary. If you're in the high-tech company, maybe I'll give a 100K bump if you have this label, this understanding, or you're a person that have a PhD. Now, which is this link here, the link from W to Y. Maybe there is some disparity. Society may be guilty, quote unquote, between the link between X and W. I'm a Google, I'm a, what's the name, OpenAI. I don't control how people in society are picking, I join the PhD or don't join the PhD, which is the link from X to W. But I can use W, in the law this is called business necessity. I use W as a criterion to decide my salary. Then, but still, there is this compounding effect from X to W and W to Y. This could be one mechanism in the world that is leading to the disparity or generating the disparity. Mechanism 3 out of 3, is about, there is some correlation there, for example, between gender and nationality. And the companies, maybe is an evil company or something like that, that is using the nationality. If you're not American citizen, maybe they are putting your salary lower because now you are more vulnerable and will be kicked out of the country. Then I'm using the nationality indirect. There is a correlation between, by the way, if you go to the data, this is true. There is correlation between nationality and gender. This is happening in the world. I look into nationality, not at gender, and I use nationality as a criterion to change salary. Now these 3 mechanisms are active. Now, after some kind of legal argument, and this happens in the world, they're not making the courtroom, this is how it goes, not formally, but heuristically, after a legal argument, the jury may be okay, may be kosher, the variations of this random variable, the variable Y, may be okay due to education. It's called business necessity in the law, as I said, but it's not okay or not kosher, the variations that are due to gender and age. Then the company cannot discriminate directly based on gender, for example, or based on age. Now the question here for us, we are trying again to explain the world, is about how to disentangle, this critical word here, disentangle, how to disentangle the variations that are within this TV. Because now TV, the number that we have there, is including this qualitatively different types of mechanisms or mechanism that could have led or could lead to the disparities in the world. Now, the number is 14K. This is true. I was right. That's good. Now, the plot in the right, the red one is just the 14K, but now the green is the direct, the one through X to Y, the blue is the X to W to Y, and the purple is the one that is the spurious one, from gender to age and nationality to salary. Now, by TV itself, this is one explanation, but this is a qualitatively different explanation. Then, in case one, maybe you're okay. There's no direct discrimination. Green is very small, it's around 0. In the second one, there is a good amount of discrimination, direct discrimination. Then the observation here that the TV, the total variation, cannot distinguish between these very two different types of explanations. Then, and TV is what we are doing in the language model or in the current TAC. And you would like to use a causal model in order to disentangle and say, no, the guys are guilty. This is the proper explanation. Or this is the explanation of how the variations are going. This is good as a general, chapter 6 in the book is all about that. Now, that I'll cite soon. Now I'd like to move about the AI itself. Can you open the AI box and try to say why the AI is predicting or doing something in the way that they are? Qualitatively different types of explanation, by the way. But let me talk to you a little bit about mechanistic interpretability, or what's the failure and what should be a causal mechanistic interpretability. And I'll give you 2 examples. I'll start with the simplest one that I could think of, MNIST. And there's a color MNIST here. And there is the color X and the digit Y, and we create some correlation between color and digit. Now you go there and take a picture. And then you have this little matrix that is the variable Y. And now you have the inferential, this is what I'm saying. And then you have the inferential set, we do inferential task that you train a predictor, Y hat. And now you come out and you want to ask why the classifier is predicting this particular color, or sorry, this particular digit. And that's the question. Can I open the classifier and say why this prediction is happening this way? And then we'll train 2 classifiers here in order to understand what I'm saying, what's the setting. The first, again, the most basic question that I can ask in ML 101, because now it's very easy, maybe not 20 years ago, but it's the easiest question. Almost the easiest, because we created, by the way, sorry, I gloss over. We created this correlation between the gender, the digit and the color that is given by, what is it? That is given by this dash bidirected arrow, just illustrated by the dash bidirected arrow. There is a hidden variable randomness that is making the digit to be, I don't know, maybe more blue or cyan when you're around 5, and kind of more whitish when it's around 0. Then it's generate this correlation between the type of digit that you are getting. Correlations are everywhere. This is just mimicking that. Now, we train 2 classifiers. One is the standard, and the other is we call robust. But robust here is that we just remove the color. We just get a grayscale. And then we have number 1. Number 2, we have 2 distributions. The training distribution, that is the one on the left, you train these 2 and you get very high accuracy. Again, the problem is too easy. Now what we do is shift a little bit the distribution. And this is what happens. There is a huge drop in performance in the standard classifier. It moves from, the problem is 99% to 18%. And now the question is like, okay, this is happening in the world, and I know the answer because I was the one that crafted, or my student. And now the question, can I open these classifiers and try to explain why they are predicting the way that they are predicting? Can I do some attribution? Let's do that. And I just got in this one, the SHAP value, that is the most common one, the most popular. There's thousands of papers written after SHAP with the different variations. I just picked SHAP because it's very symbolic, very important, but it's the same. There's a heritage there. Observation for us, because we already understand. SHAP is a layer 1 type of method to try to explain in the mechanistic interpretability literature. Now, and this is what SHAP says. Here's the plot. The x-axis are the digits, and the y is a measure of attribution. And blue here, that is the true digit, meaning I'm saying that is a 5. Now if you go to the standard there, and the blue is very high, it is a 5 because of the digit 5, and it's not because of the color. Now, the same thing happens with the robust. They are relatively very similar in reality. Now, in other words, based on the SHAP, if I use SHAP or any variation of that, I cannot distinguish these two classifiers. There's no explanation coming out, which is not surprising in some way, because this is just a layer 1 quantity. Now let's use a layer 3 quantity, the counterfactual version of that. And this is what we get. There is the standard classifier there, and the standard is saying that I'm saying that it is a 5, and then you have the yellow there. I'm saying because of 5 because of the color, and not because of the digit. Then we're doing the proper, it's wrong, of course, but we are able to open and differentiate. Robust, of course, is still 99%. It's saying because of 5 because of the digit 5. It's getting it right. Now, I see hundreds, maybe thousands now, but hundreds even in this conference here, maybe dozens at the moment, or at least hundreds if you accumulate mechanistic interpretability, using SHAP of evaluation of layer 1 quantity. And you have a supercomputer, you spend money, you spend the lives of our PhD students, the researchers, and there is zero chance that we get the right answer, because it is a layer 1 quantity. The explanation is not good. We need to go to layer 3 and get this more fine-grained degree of understanding. Now, to conclude, I would like to move towards this is a simple classification task. Let me move to something slightly more interesting, that is same idea in a complex sequential setting, where the goal is to identify the root cause of a world model. This is the paper that just came out. We just put it out. But we have something turning in the world model. And this is the game of Pong. Again, the simplest Atari game. We can scale that. We're scaling now from color amnest to Pong. Next, we can discuss what are you scaling to a larger scale. But you have now the right quantity. The game becomes different. The game now is scaling. It's not only semantical now. Thing that is usually overlooked here by some of us in the community. Semantics is now we are chasing the right quantity. Now you can play scale. Otherwise, we're just going around ourselves here, around our axis, right, our own tail. Now, you train in the Pong, we have a world model, and you train it, and then you get a return, let's say 21. Whatever number is that, but let's say a high reward here in this case, not very hard. Now you move the systems that you train there to the real world. What's the difference between the real world and the world model? Simplest thing that we could think about, let's do some blackouts. Random blackouts throughout the game. There is a little deviation. The world model is not perfect. I believe that it's very far from perfect, but let's do just minimal variations, perturbation. And that's what we got. We got kind of significant drop in the performance here from 21 to 15. And now the question is about, can you explain that? Why is it happening? Because AI is making these decisions, how would you play the game? Now, if you plot here, this plot is the x-axis is the transitions, the steps that you have, in the y-axis is some kind of measure about saying, this step was the one we are doing credit assignment, is a little bit been uniform, that Raul was saying, but it's still very kind of not good, that each spike there that is orange is saying, this was the step that was guilty, this was the step that was guilty, this was the step that... In other words, all over the place, the signal saying that this transition was the one that led to the disparity that you are seeing there between 21 and 15. Now, if you use a causal layer 3 method, same idea of the amnesty, same quantity, just scale up version. There's a lot of dance about how to do that, non-trivial. But once you do that, you get very precisely the blue points. There are 2 particular transitions in this case that led to this significant drop. Then you are able to pinpoint the causes or the reasons about the drop. This is just before I finish, this is just a video about, you see, you have to do the blackout. This is just playing the Pong. You do the blackouts, and in the bottom, you are kind of plotting exactly the algorithm, the SHAP or the variation. There are different ones here. And transition is coming, but it's a particular, where is it? Where's my mouse? Give me a second. Oh, is my inability, Yeah, my mouse disappeared. It's here. But attention here, because this is a 0.500 and something, that is do you see this step? Now if you go back, it's hard. If you go back, now you can expect why our algorithm, the causal one, is saying that this 500, maybe I can share, but it's about the pedal is close, but not close enough to the ball. Then this is exactly the time that we needed to know where the ball is, because we have some kind of degree of freedom and your movement will matter. If the ball is too far and you do the blackout, it doesn't matter, because I can move towards there when the blackouts come out, right? When I can see the screen. And if it's too close, the ball and the blackout happen there, it doesn't matter, because the ball will hit anyways. The point is about when there is enough distance and I don't have enough time to recover. The algorithm is able to pick this up, which is quite remarkable, it's quite good. And anyhow, this is the name is counterfactual root analysis, but in reality, we're doing some kind of understanding about why the AI is doing the way that they are. Scale now is about, let's get a bigger model, a language model, small one, and apply the scale up this type of method. But we know that we are chasing the right quantity. Now to conclude, I would say that there is a underlying theme here about everything that I'm saying today. And I think this is a proper way of seeing it, that fitting is different than understanding. A model can fit the data extremely well, reproducing everything that we observe without knowing why it happens. When this is the case, it may behave correctly. This is interesting. It may behave correctly as long as the conditions remain the same. But we may intervene in the environment. The moment that we intervene in the environment, the moment that we move to a new environment, a new reality that you didn't collect the data, or you ask a question about a counterfactual, about an alternative version of this world, then the gap becomes real between these things. Then fitting is about correlation, understanding is about causation. Now, another way that I like to see that, I think is a very, very good slide. I was very happy that I wrote, that today I like to think about these two axes, this 2D plot. Then you have this x-axis is about what I called before the linguistic fluidity. The systems are doing this extremely well. We fall in love with it. It's quite, again, mind-blowing. Now, if you go where we are at the moment, we are here, in the LLM world is here, in the yellow. And if you keep moving in our directions, OpenAIs and Anthropics and so of the world, nothing in bad. Natural movement, not nothing bad, personal. But natural movement is kind of improving this linguistic fluidity, or how visually compelling. We have images that are mind-blowing, or videos that are so cool. We are moving in the X directions. Now, people doing causality, I am an example, or Pro is an example. We are here in the Y-axis. We are trying to optimize or understand what understanding means and formalize there. Brittle in the sense that it's very mathematical. It's very good, I'm excited, but there is no language there, or the nuance of language. And had we continue our natural movement, we are going the Y direction. Now, what I propose here is about, we should have both, the best of both worlds in a way. How do you combine these capabilities and move towards causal AI? That's the program. And turns out not to be trivial. Those are very different languages. You cannot just slap causality on top of that. You can put band-aids, by the way, I usually say. In the Frankenstein, try to let it move. It has a nice makeup, a nice dress. But still, I was saying the US, what is it? If you put a lipstick in the pig, it is still a pig. The same idea, I'm almost done. Then just to conclude, how we move towards this unified system that is very two different languages. Our goal here, let me close with the research program. The goal here is to develop more general and trustworthy AI endowed with the following capabilities. Again, number one, they have causal and counterfactual generation. Number two, they're able to have causal understanding and be able to articulate explanations. You spend good amount of time here, not a lot, but a good amount of time here today in these two capabilities. There are others. Third one, I mentioned in the beginning, they should be more efficient and precise in terms of decision-making. There is the whole causal reinforcement learning world to be explored. They also should be more generalizable and robust across these different conditions and changes in the world. And they should also be able to do model learning and discovery. Invitation here to think about that. Causal hierarchy is not just a conceptual organizer. It's some kind of principle about how should you build the systems. I kind of giving my 45 minutes or 47 on this one. This is all in my book. The draft of the book, most of it in the book, the draft of the book is causalai-book.net. It should be in print in the end of the year, as far as in the MIT Press. I'm just one of the speakers. Thank you for the funders, and this is a huge effort for many people. In the left is my research group at Columbia, and the right are kind of external collaborators. Thank you very much. Happy to take questions.
So thank you very much. Before we get to the questions, is there a chance that one of the authors for the landmark workshop paper is here? If so, please quickly talk to Katharina over here. Otherwise, we can proceed with the questions.
Thanks for the talk. As I'm sure you know, language captures sometimes like causal reasoning, right? We can, and you know, the large language model is trained on language. And so do you think we can think of this as like some kind of amortized inference, right? But when you fit a language model on those sort of causal reasoning traces, do you think the model could sort of acquire maybe an imperfect, causal capability, if that makes sense? So I think there's maybe a little bit of that happening with current models.
The two things. One, yes, I like to think about, we can, not in the tone that is considered today, but yes, the overall repository of world's knowledge, including causal knowledge, is underlying the systems, right? The systems are trained with that. Then there is causal knowledge. Then if I think about the language model as a database of some sort, more fancy, and there is a fluidity of language, as I said, then yeah, we should leverage that. And there are ideas about how to do that in order to extract causal relations and start kind of warming up a causal system. That's true. The other side, just the balance is like, again, Raul is giving examples like that, but if you go to physics 300 years ago, and you get everything that is written in the world, and then we train based on that our system, we'll be saying that the sun is revolving around the Earth, or things like that, and with a lot of confidence, and people will be believing, and this may be not true. Then how can you kind of distill that or have the sensibility for that? Not popularity, context doesn't give us the truth, and I think it's an important point. But yes, in principle, we should leverage the fragmented type of causal knowledge that is under no-brainer. It's a good idea.
Thank you.
So we have time for a final short question.
Hi, thanks for the talk. One question. What do you think is
Speak a little bit louder if you can.
What do you think is the role of structured representations, in the sense that representations that can align state affordances or other properties of the world, so they have strong inductive biases?
Right. Yeah, the note here, two things again. At least more traditional causal inference, we do have some way of specifying some type of knowledge about the world. There is some kind of strong inductive bias. We do with causal graphs or variation, not only, but variations of that. Then this gives us some glue or some hint that there is an inductive principle there that allows us to reason across the different layers. In the book, we start with a negative result and possibility, saying we cannot move across the layers with zero knowledge. It's a no free lunch that we are kind of used to, which I think is very good. Then the whole discussion in the book becomes, okay, but now which kind of inductive bias would need in order to start kind of gluing or start doing inference across the distributions? Then there are different types of different versions of doing that. And I think you learn a lot through the sciences. Now, which is good, the science meaning every other, I usually say, every other building in the university that is not the computer science building. Now, because they are doing causal inferences, or trying to do at least causal inference, sometimes succeeding. But now the question for us is about how to understand these principles and also scale it up. Because we will not do case by case. We have scale that is kind of millions of variables and it's very huge. Then this is kind of the current challenge. I think that is an invitation for you and others here to understand, even to understand the problem, and then maybe helping to solve it. It's a generational challenge in reality.
Thanks.
Yeah, thank you.
Let's thank the speaker again. Okay, now this concludes the invited talks. Now we should have 2 oral talks, but is by chance the speaker for the landmarks paper here? If not, we skip the next talk and we immediately go to the next talk.